Hello guys, in this video I'm going to summarize for my parts which is covered in the final exam question, which is fluid dynamics. I hope that this video won't take a lot of time, so that at least you can take a look at another video which I'm going to discuss quiz number 3 together with the selected previous final exam question. It's going to be video 2 and 3. So for my part, it's actually a fluids dynamics. As I said during the lectures, the difference between my parts with the Dr. Anas part will be Dr. Anas is covering on the fluid statics. By now, you should be able to differentiate between fluid dynamics and fluid static. Example of the fluid dynamics will be, for example, let's say I have a pipe, just like we've done during our experiment 4, 5, 6, and 7. Let's say we have a water, and then the water was actually flowing inside the pipe. Because the water was flowing, therefore, it is what we call a fluid dynamics. Example of the fluid static will be, I have a tank, and then inside the tank here, it was filled with, let's say, a benzene. Obviously, the benzene inside the tank over here is not really moving. Therefore, it is what we call a fluid statics. I'm not going to cover on details on the fluid statics, but a great deal of attention will be given for the fluid dynamics. I'm going to draw a pipes. So let's say I have a pipe. Let me use different colors. Let's say I have a pipe look something like this. Inside the pipe, and again, I'm going to have a water flowing. Let's say I'm interested between these 2 points. Let's name it as a point A, and then this one is a point B. So the water was flowing from the point A to the point B. From the principle of conservation of energy, we can say that the total energy at the point A should be equal to total energy at the point B, because the principle of conservation of energy stated that energy cannot be created or destroyed. It can only be changed form. What I can say here is, most probably, let's say the total energy here at the point A here is going to consist kinetics energy, potential energy, together with the flow energy. Most probably, the kinetics energy at the point A is not going to be equals to total energy at the point B. Why? Because the pipe has a different diameters, therefore, the velocity is going to be different, and also we know that kinetics energy was actually depending on the velocity of the fluid. Therefore, but still, in the end, the total here should be equal to total at the point B. So from the principle of conservation energy, we actually end up with the what we call a Bernoulli's equation. This one is not given. Then you have to memorizing it. Let's take a look at every single terms inside the Bernoulli's equation here. In here, we have PA, which is reference to the pressure at the point A. And then we're going to have gamma. Gamma is the specific weight, which is equals to rho multiplied by G. That's why sometimes we use rho multiplied by G over here instead of gamma. And then we have Z. Z here are reference to the potential energy. Potential energy here means that the Z here is just the elevation. And then the unit will be meters. And then we have velocity, power of 2 divided by 2g. So this is what we call the Bernoulli's equation. And of course, the Bernoulli's equation here, even though it was widely used in the industries, but still, they made a lot of assumptions. One of it is, for example, they assume that the fluid is incompressible. What does it mean? The fluid is incompressible, meaning that even though the water, for example, water here, are traveling from the point A to the point B here, the density won't be changes, meaning that the density remain constant. That's why, if you notice that here, the gamma here, or the rho g here, I'm not going to say that the rho at the point A multiplied by g, rho at the point B multiplied by g. Instead, we just assume that the rho are the constant, the same. Therefore, the gamma here, we just use the gamma and gamma here instead of using, gamma A and also gamma B. So this is one of the assumption we made in order for us to apply for the Bernoulli's equation. Another assumption we made is we assume that there's no energy losses due to friction. Because this is chapter 5, and then in chapter 6 we actually did consider the energy losses due to friction by adding up another term which is minus HL. But for the initial Bernoulli's equation, we just simply assume that there's no energy losses due to friction, even though in the real life usually you should consider the losses due to friction. What else? We also assume that no heat energy transfer in or out from the system. So if you really understand what we learned during our thermodynamic subject, you should notice that in thermodynamic we do have Q, which is energy transfer into the system, or sometimes we're going to consider Q out from the system. Usually Q in is going to be positive, and then Q out is going to be negative. That's what makes the thermodynamics slightly difficult. But then for the fluid mechanics, usually we just simply assume that there's no heat energy transfer in or out of the system, meaning that the temperatures here are actually at the constant temperatures. And also, we assume that though mechanical devices is installed in the pipes. Mechanical devices here are usually referred to the pump, because whenever you install a pump, actually you are supplying an energy, because once you install a pump here, some energy will be supplied to the system here. Therefore, energy at the point A won't be equals to energy at the point B, because the pump here already supplied another energy. Therefore, energy at the point A plus energy supplied by the pump should be equals to energy at the B. And again, this one we just simply assume that there's no mechanical devices or pump was installed inside the pipe. So this is the 4 assumptions we have made in order for us to apply for the Bernoulli's equation. So now we already end up with the first equation, which is Bernoulli's equation. So let me erase it first. So, and again, I'm going to draw the diagram here, and again I'm going to use the water inside the pipe here. Water was actually flowing. So from energy equation, we're going to say that we're going to end up with the Bernoulli's equation, which I already explained every single term over here. And also, we can also apply for the principle of conservation of mass. We should say that this is what we already learned in our PCB subject. We can say that whatever the mass is entering at the point A, or MA, should be equals to whatever mass coming out at the point B here. This is what we call a steady state. This subject is should be easy, because in PCD subject, process control and dynamics, usually we consider the Sometimes whenever we have a mass entering here, it's not necessarily all the mass here is going to become out here. Sometimes it was accumulated inside the system over here. So this is what we call unsteady state. But then for fluid dynamic, we just simply assumes that the mass is conserved, means that whatever is entering through the point A should be equals to whatever comes out at the point A in terms of mass. So I can say that because the mass was flowing, therefore I'm going to use mass flow rate. Mass flow rate at the point A should be equals to mass flow rate at the point B. And then the mass flow rate here with the unit of kilograms per second. And again, because it was a fluid, it's quite difficult for us to measure the, what we call it, the mass which is flowing. But instead, it's easier for us to measure the volume or volumetric flow rate. Volumetric flow rate will be the unit of, the volumetric flow rate should be Q. Volumetric flow rate with the unit of meter cube per second. So from here, in the unit conversion itself, I should say that mass flow rate with the unit of kilograms per second should be equals to volumetric flow rate with the unit of meter cube per second. How do I get kilograms from here? So actually I have to multiply with the kilograms per meter cubes so that I can cancel out my meter cube here. I can cancel out my meter cube here. So I end up with the kilogram per second. But then kilograms per meter cube here was actually equals to density. So I can say that mass flow rate is actually equals to flow rates multiplied by density. So this equation can be rewrite as Q at the point A, flow rate at the point A, or volumetric flow rate at the point A multiplied by density at the point A should be equals to flow rate at the point B multiplied by density at the point B. But then, as I said before, usually for the fluid dynamic, we consider the fluid was incompressible. What does incompressible mean? Means that the density won't be changed, meaning that rho A is going to be equals to rho multiplied by B. So now I end up with this equation. QA equals to QB. Flow rates at the point A, as long as the fluid was moving or flowing, the flow rate at the point A should be equals to flow rates at the point B. Therefore, I have another equation. I can always apply this equation, as long as the fluid was flowing. And also, the unit for flow rate, and again, was meter cube per second. And then, I also know that flow rate was actually equals to meter cube per second. And then I have a velocity because it was moving. Therefore, I'm going to have velocity of meter per second. If you notice that these two equations can be related between one another, because this one on the left side was meter cube and then this one was meter. So I just simply multiply by meter power of 2. I'm going to end up with the meter to power of 3 per second. So meter power of 2 was actually unit for the area. Therefore, I can have another equation which is Q, flow rate, equals to velocity multiplied with the area. Please note that for the Bernoulli's equation here, I have velocity. If the flow rate was given, I can always use this equation to find the velocity. Same goes here. If let's say I have a velocity, by multiplying with the area, I can always get the flow rates. So this is how we memorize our equation. So this is another equation, equation number 3. And then by combining these two equations, I actually can rewrite this equation as flow rate QA equals to velocity at the point A multiplied by area at the point A should be equals to velocity at the point B multiplied by area at the point B. So this is another equation, which is equation number 4. So this is the 4 equation which I need to remember for the first part of the lecture, which is on the Bernoulli's equation. So now I already have 4 equations, and then I'm going to move into the chapter number 6. In chapter number 5, we did assume that, for example, this Bernoulli's equation, let me write down here. For chapter number 5, basically what we learned is we actually derive this Bernoulli's equation And again, as I said before, this Bernoulli's equation made a lot of assumption. One of it was they assumed that there's no energy losses due to friction. Therefore, in chapter number 6, we did consider the energy losses due to friction. How does this occur? Let's say I have a pipe over here, and then I have a water flowing. Definitely the water is going to fill up all the diameters of the pipe over here. If you notice that some of the pipe was actually in contact with the pipe wall, therefore it required some of the energy to overcome the friction because it was in contact. Therefore, it's going to have a friction. So some of it will have to use the energy to overcome the friction. That energy is actually has to be minus because that energy is going to be lost. So this is what we call energy losses due to friction. So for the HL here, you can obtain the value of HL by using Darcy equation. HL equals to F multiplied by L over D multiplied by V squared over 2G. Going back to this diagram, let's say this is my point A, this is my point B. So if I want to find how much is energy being lost due to friction, I can use this equation. Only that, if you notice that for the Darcy equation over here, one of the term was diameters. Therefore, if I want to find the energy losses due to friction between A and B here, I cannot straight away use this length. Let's say the length here was 10 meters. I cannot straight away use it because the diameters is different. See, the diameters here is smaller compared to the diameters here. Therefore, if I want to find the energy losses due to friction, I need to find it individually for the same pipe diameters. Meaning that I have to find the HL1 here, and then it's going to add up with the HL2 because of the diameter is different. Otherwise, it's going to be confusing which diameter to use because let's say this one was 100 centimeters, this one was 200 centimeters. So we have two different diameters. Therefore, you have to use it individually. So by taking a look at the Darcy equation here, all the term is quite familiar. For example, L should be the length, meaning that the length of the pipe here, let's say from here to here, what is the length? And then of course we have 2G is a constant, 9.81, and then we have velocity. Velocity also straightforward. Sometimes they give in the form of flow rates, and then I also know that the flow rate was actually equals to A multiplied by V. Therefore, if I want to use the velocity, I have to divide the flow rate divided by the area. Then I'm going to get the velocity. The only term which is unknown here was the friction factors. The friction factors here is slightly new for the chapter number 6. The friction factors here can be obtained either by using formulas, simple formulas, 64 over Reynolds number, or I can also use Moody's diagram. Can I use either one? The answer is no. In order for me to select the correct methods to find the value of F was, actually I have to determine the type of flow just like what you did in the experiment number 6. So, type of flow. You need to determine type of flow. To determine type of flow, actually you can use the Reynolds number because Reynolds number given equals to rho density multiplied by velocity multiplied by diameters divided by dynamics viscosity. Sometimes they give in the form of this is dynamics viscosity. Sometimes they give in the form of kinematics viscosity. So if they give me kinematics viscosity just like chapter 1, I can use another formula because Reynolds number equals to velocity multiplied by D divided by V, which is this is the kinematics viscosity. Because from chapter 1, I also know that kinematics viscosity equals to dynamics viscosity divided by rho. Therefore, I can substitute this one into this one. So I'm going to end up with something like this, which is velocity multiplied by d divided by v. So for the Reynolds number, if you found that the Reynolds number was less than 2000, therefore it is a laminar. Because it is a laminar, I can use this simple formula. And then if the Reynolds number was actually greater than 4000, therefore I have to use it is a turbulence. Because it was a turbulence, therefore the easiest method was to use the Moody's diagram. Most of you actually are doing well for this part of question. It's not that difficult, but sometimes we have to memorize a couple of equations. Test number 2, question number 2 is a good example on how the question on the energy losses due to frictions look like for the finals. So I hope that you can refer back to that question, because I already shared with you the marking scheme for the question. So now we already considered the energy losses due to friction. So now our equation looks something like this. And then in the chapter 6 part B, we actually introduce another term into this equation. Another term was what we call a minor losses. So now my equation looks something like this. My very much the same equation, which is Bernoulli equation, but then I'm going to extend it a little bit. So now I have PA over gamma plus ZA plus VA squared over 2G, because we already covered the HL minus HL, equals to PB over gamma plus ZB plus VB squared over 2G. And then now I'm going to add minus another equation, what we call a minor losses. So the minor losses here, the formula is quite simple. The minor losses HA is actually equals to K multiplied by V squared over 2G. And then HA, of course, what we call a minor losses. And then we have V, which is velocity. And then we have K, which is resistance coefficient. The K value here is actually depending on the type of pipe fitting. For example, let's say we have 90 degrees elbow. Sometimes we have an entrance losses, an entrance from the big tanks to the pipes. This is what we call entrance. So, but this one you don't have to memorize on, what's the value, etc., because this one is given. So if you notice that here is a solid, I'm going to use the same appendixes which I'm going to use for the finals. Yeah. So number one, you're going to take a look at this one, figure 1A. Figure 1A is given the resistance coefficient, which is represented by the symbol K, for the different type of pipe entrance. So this is what we call an entrance losses. The entrance losses, let's say in the question they did describe about the pipes was actually, the pipe used was an inwards projecting pipes from the large tank. So definitely I'm going to use this data, and then the K value is going to be K equals to 1. Therefore my formula is going to be HA for this area equals to 1 multiplied by VA. Let's say this one is a VA power of 2 divided by 2G. And then sometimes you can say that, the pipe used was actually square H inlets, and then the K here is going to be 0.5. So this is what we call an entrance losses. And then we also have, this is the Moody's diagrams. Yeah, I'm not going to take a look at the Moody's diagram here. And then sometimes we can also have the valve and etc. Okay, for the valve here, it's slightly different, yeah, because you will take a look at this, you're going to be given this table. Yeah. So for the valve of fitting, the K here can be obtained by using this formula. K equals to F multiplied by T multiplied by LE over D. FT here was actually can be obtained from here. Usually they're describing the pipe with the nominal pipe size was 1 inch or usually 1 inch or 2 inch. So this one is nominal pipe size, and then from here you can determine what is the value of friction factor, which is FT. It is not the same as F, yeah, but then it represent the FT. FT was actually the friction losses due to the pipe sizing. So this one is just using the table 4.1, and then LE over D here was actually depending on this one. So table A2. So let's say they are saying that okay, the valve used was a gate valve fully open. So the gate valve fully open is going to be LE over D is going to be 8. I'm asking about my dash cam. Alright, so now it's going to be LE over D is going to be 8. Let's say my pipe fitting was nominal pipe size was 2 inch. Now my FT is going to be 0.023. So I just simply multiply by 0.023, multiply by 8. It's going to be certain value. So this value is going to be my K. And then once I already get the K here, I can calculate for the HA. Meaning that, let's say my diagram looks something like this. So this is I'm going to install a globe valve over here, fully open globe valve. So I can calculate for HA over here equal to K multiplied by VA squared over 2G, meaning that velocity here, VA. So K multiplied by VA over 2G. But then I also know that for the globe valve, K is actually equals to FT multiplied by the FT multiplied by LE over D. So but then for the globe valve fully open, LE over D was 8, FT was, let's say, 2 inch, is going to be 0.023. So this is my value of K, and then I just simply multiply with the VA. Then I'm going to get how much is the minor losses for this one. So this is what chapter 6 all about. So now let me erase everything first. So now, in chapter number 5, we have Bernoulli's equation. Looks something like this. And then what happened in chapter 6 is, because this Bernoulli equation make a lot of assumption. One of it was no energy losses due to friction. And then chapter 6, we're going to consider almost a real condition, meaning that we're going to consider the energy losses due to friction. Now, my equation have another term, HL equals to PB over gamma plus ZB plus VB squared over 2G. Sometimes in the industries, we also have to make a lot of pipe fitting. For example, due to the constraint, etc., we have to do the 90 degrees elbow, etc. Therefore, this is what chapter 6 is all about. So now in chapter number 6, we have another terms added into the equation in chapter 6a, meaning that we're going to have minus HL minus HA equals to PB over gamma plus ZB plus VB squared over 2G. And then for chapter 7A and 7B, the question is all about this full equation, meaning that we're going to have the full piping system, and then you have to apply all these equations to solve for the either chapter 7A, which is the serial pipeline, or 7B, which is parallel pipeline. To recap, what's the final exam look like? Question 3 and 4 are actually optional. So this one is going to be question 3B, And then this one is going to be question 4B. And then this one is going to be question number 2. Question 2, 20 marks. But then for question 3B, it's going to be 10 marks. And then question 4A is going to be 4 marks. This one, I'm going to cover it in the video number 3. Because for the video number 2, I'm going to cover this one. I'm going to use the quiz number 3 as my example of question, and then I'm going to try to solve it. That question, all the question in the quiz number 3, so that I can discuss a little bit on how to attempt that type of questions. So I hope the video will help you to have a general overview, because this one we covered for almost 6 weeks. Almost impossible for me to cover it within 40 minutes. Thank you.